Starting today, we just have an exponential function. It has a number called the base raised to a power. It says the independent or input variable is the power. So that's a good way to put it. So independent or input variable is always going to be the exponent. So we might call it an exponent instead of a power, but that's the idea. Okay. And it says ka to the x plus c. So we're usually used to seeing something that's like 2 times 5 to the x minus 4. We might see something like that. Or y equals, let's see, negative 5 times 1/2 x plus 1, something like that. We're used to seeing those types of equations. All right, where it says, oops, it wouldn't be negative 5, sorry, it'd be a, oh, no, it's fine. Yeah, where it says the a, the a value is always greater than 0. So that's the value that's going to go in here. Or we'll do that in a different color. So that always goes with the exponent. And then the other important thing is that the k value is never equal to 0, just because otherwise you would just have y equals negative 4. You'd have a straight line because you'd have 0 times something. Those are the types of problems we dealt with exponentials last year. E is an irrational number with the value of 2.71828, and then I think it goes 1828, 1828. Just keeps going on forever. We might remember this is just the form of like e to the x, y equals e to the x. So e is a number, not a variable. That's the real key there. And then the last one, exponential functions can be used to model real-life situations where there is a constant percentage change. So we use exponential functions in stuff like financial math. That's the big one, which we talked about last time. We also use exponential functions with exponential growth or decay. The big decay example we usually have is half-life. All right, those are the types of situations we would see. Okay. All right, so the first example today, we'll just dive right into it. It says for each of the following functions, find the equation of the horizontal asymptote. So that's going to be a y equals equation. Always write the horizontal asymptote, or if it's a vertical asymptote, always write it as an equation. Okay, so you said the file will not load for you on your Chromebook. Let me email it to you real quickly. Let's see if we can fix that. That's an easy fix. Hang on just a second, yeah. So the 3 things we're gonna look for: asymptotes, always write them. If it's a vertical asymptote, x equals. If it's a horizontal asymptote, y equals. The coordinate of the points where the curve cuts the y-axis. So in other words, that's the y-intercept. And it does say the coordinates, which I like that, because whenever we're talking about y-intercept, we do want to write an ordered pair. And then it says state whether the function is increasing or decreasing. So big things we want to look for on these types of problems. The horizontal asymptote is always going to be a number that's being added or subtracted at the end. So in this case, with these exponential equations, it's going to be like that plus 2. Because the horizontal asymptote, the parent function, starts at y equals 0. And then whatever the plus 2 is would be raising that horizontal asymptote. Or in part B, the minus 2 would be, or the minus 3 would be lowering that horizontal asymptote. So for this first problem, part A, the equation would be y equals 2. And on this one, it'd be y equals negative 3.
Just realized mine is like, it doesn't have the problems on there. It just has like the I and I, but there's no problem on it.
Did I accidentally load the
Oh, yeah, it's a doc.
I accidentally loaded the doc instead of the PDF. Okay, let me fix that then. Sorry about that, you guys. Where were we? So we finished the horizontal asymptotes. Finding the y-intercept. Y-intercept ordered pairs are always going to be written as 0, comma something. So that means we need to plug in 0 for the x value. So 3 to the 0 plus 2. And that's where the y-intercept is going to be. And this one's going to be 5 times 0.2 to the 0 power minus 3. And we'll set them as y equals. Oh, come on. I can do this better. We'll do this in a different color. So that way it separates from part A. So part B, y equals 3 to the 0 plus 2. Part B, 5 times 0.2 to the 0 minus 3. Well, anything to the 0 power equals 1. So we're going to get 1 plus 2 there. And here we're going to get 5 times 1 minus 3. 5 minus 3, we're going to get 2. And here we're going to get 3. So the y-intercept for part B is going to be 0, comma 3 and 0, comma 2 respectively. Always make sure that you write down these intercepts as an ordered pair, especially like on the IB exam. You want to make sure you're doing that correctly. Last part, part C, are the functions increasing or decreasing. To find that out, we got to look at the leading coefficient, so the number in front here. So in this example, it's a positive 1, and in this example, it's a positive 5. That means it's going to be increasing. If you're not sure, you can always graph it on Desmos. That's always a safe bet to do it. But in these examples, it's going to be increasing. All right, positive number means it's increasing, a negative number means it's decreasing. All right. Chocolate oranges? Like the oranges that are dipped in chocolate? I don't even know Terry's chocolate orange.
No, it's Terry's chocolate orange. It's like chocolate in the shape of an orange. That's like cut into slices, and it like has an orangey zest to it, I guess.
Oh, okay, yeah, I've heard of that before.
Is that a British thing? Because I feel like
Yeah, it's completely like the most British.
Dollars in a bank that pays interest rate of 4.5% compounded monthly. Okay, sketch a graph to model how Bailey has, how much Bailey has in the bank after X years. So the first thing you'll want to do is you want to like come up with the equation. So that way I can sketch the graph. So this one we're going to need to do the principal value, or the present value, I should say. Remember, we have the future value and the present value. So y is our future value here. And then we do, what was this part? It was the 1 plus, it was the 1 plus your rate, 4.5 over 12 times 100. And then to the 12 times x power. That's how we'd want to write this one down. Okay. And you got to write it down as a y equals and put the x there instead of the n, just because you want to be able to sketch it on a graph. Okay. So then you can go to Desmos or use your graphing calculator to sketch it. And I'd recommend practicing on your graphing calculator again, because you're going to need to change your viewing window so you can see this. For example, it's a bank account and the starting value is $2,000. So you're going to want to start at $2,000 for your y, and then it's only going to go up from there to whatever your future value is. Okay? So that'll help you get a good idea for the sketch. And the x value is going to be based on months. All right. Or actually based on years, sorry. It's 12 times x. So if I were to sketch something, Again, you'll probably want to start your window around 2000 because that's where you're going to start at time 0. And then it should make some type of exponential growth from there. All right, going up in terms of time. So we'll say like this is 5 years or something. All right. And that's kind of what this will look like when we sketch that graph. And to deduce whether an exponential model is a reasonable choice to model how much she has in the bank. Okay. I don't know. I don't like that question very much. But basically, we're saying, yeah, this is an exponential model. I mean, it is going to grow more and more the more money she has in the bank. It's going to grow faster. And then calculate how much money Bailey has in the bank after 4 years. So then we would just take our equation from up above. And we're going to plug in 4 for the x. You could also use that, you can use the finance program on your phone if you'd like as well. Oh, not on your phone, but on your calculator if you'd like as well. Okay. And then that finance program will actually be useful for the last problem because now it's saying how long will it take to get to $3,000. So in that problem, you can actually set it up the other way. Instead of having to use logarithms to solve, you could do that. And you could set this up in your calculator. Or you could graph, like I said, graph y equals 3,000, since you already have the other graph, and look for the intersection. And it'll get you like the number of years you think you need. Okay, that's it for example 11 there. And I want to say it was just over 9 years, I think, is what we came up with. Okay.
What was the answer for part C?
Oh, for part C, oh, it should come out to like 20. It was like $2,300, almost $2,400. I had $2,393. Let's see. $2,393 and 63 cents. So if you plug in the 4 there, all right. All right, so last example today says Saul buys a tractor for $51,000. The price of the tractor reduces by 8% each year. Find the price of the tractor after 2 years. So the first thing we want to do is we want to say if we had 100% and it's reducing by 8%, it's really reducing. It's going to be like each year we're going to have 92% of the value. So if you think about it, like after 1 year, you'd say 51,000 times 0.92, and that's going to give you the value after 1 year, which is $46,920. And then I could do it again, 46,920 times 0.92, and I'm going to get $43,166.40. So that's a quick way to do it if you're not sure how to set that one up. All right, there are formulas for that. There's an exponential decay formula that we could use. And I want to say, is that a calculator problem? No, that one did not have a calculator example in the book. Okay. So that's what it would look like after 2 years. Okay. And then if we wanted to keep going, like we would have to do something else. Let's see. I think this one actually also reminds me of I think it's going to be an exponential problem where we would say to the n power, where n is the number of years. It kind of throws us back into those probability problems where we would say those circumstances that happen. All right, so we could do that as well, 0.92 to the n power. But if you're not sure how to do it, if you don't remember that like exponential type of equation, then what I would recommend doing is just literally just do year 1, year 2, year 3, year 4, as many years as you need to do. It would take a little longer that way, but you could do it this way as well with the 51,000 times 0.92 to the second power, and you'll get the same answer. Okay? And then just find the number of years until the tractor is worth half its original value. All right. So I could do this again, 51,000 times 0.92 to the x. And then half of that value is 25,500. So graph this one, graph that one, find the intersection. And the intersection should be an ordered pair, something comma 25,500. All right. If you wanted to solve for it algebraically, you could as well, where you just write the equation 25,500 equals 51,000 times 0.92 to the x. All right. And then you would have to use logarithms to solve that way. All right. Which in that case, you'd get 1/2 equals 0.92 to the x. And then you take a log of both sides. And then you can drop the x out in front. You guys might remember that. And then you just divide both sides by log of 0.92. And you solve for your x algebraically. So you could do it either way, whichever method you prefer. All right, but both of them should work.